Oh, you're going home to see family?
Oh yeah. It's my mom's 60 birthday. Like,
So she would
She's
rather
got
have
60.
you there for her birthday, even if it kills you.
yeah, it's the extreme opposite. yeah.
You should really hold this over her head.
Oh yeah. And my grandma is becoming 90.
I'm-
90.
I risk my life to come home for your birthday.
Pandemically. Yes. Until you find a guy with a mask and a plane and start freaking out. Oh my gosh. How's that gonna work, Dr. Bolinski?
What?
Online classes.
Well, I sent you an email
Oh yes.
yesterday.
So we're having like questions for you
So-
last time?
So what I will do is, I already have all the PowerPoints prepared and things like that. So what I'll do is over spring break, I will convert those into a set of screencasts. It's basically just me sitting at my computer,
Talking about the terms.
recording the screen, taking you through the same information that we would go through in class.
So what's a screencast? It's not like there's a person, it's like you're talking to the slide.
I am talking to you
Oh,
while
I'm talking.
while you can see the slide. So-
Okay.
It feels like your classes.
Okay. The
It goes
visual
over, yeah.
is
The
the
visual
slide.
is gonna be this.
Okay.
I'm experimenting with the method by which I can flip back and forth from, the slide to a whiteboard. So
Okay.
I'll probably do most of these in my office, so that when I need to draw things on the whiteboard, I can. But basically, what I'm probably gonna do is I'm probably gonna end up altering I'm probably gonna end up altering all of my PowerPoint slides so that things that I would normally be writing on the wall, on the whiteboard, are also in the PowerPoint, so that I don't have to do as much shifting back and forth as possible.
If you could solve the how to point to it thing.
Yeah, I'm experimenting, so, here over the weekend, probably I'll be experimenting with a different, screen recorder. So what you do when I've done this in the past, I've used something called Camtasia, which is kind of limiting. All it does is it basically takes whatever section of your screen you're interested in recording, and it records that section of the screen. There's a new thing called Bloom that allows you to then write on the screen as you're recording and things like that. So I'll experiment with a couple of things here pretty quick. But I've done screencasts when I've had to be out of town for a conference or something and I still want to deliver material. I've done screencasts in the past when, something didn't go particularly well in class and I wanted to clarify it before we come back to class the next time. For my first year students, when they do their statistical analysis for their first year research project in evolution and ecology, I'll do a screencast that walks them through their entire analysis so that they can understand. They're not yet at the point where they can do all that themselves, but we provide them with an R script and then we walk them step by step through the R script so that they can figure out how to operate it.
Yeah.
So I'm familiar with screencasting. It's just a video. You would watch it. I'll put it on the YouTube channel just like I have with the class videos. And then what I need you guys to do is I need you guys to view those before the day that we're gonna cover that, so that when we meet virtually, and my plan right now is to use Zoom meetings. Zoom, I sent you guys a invite to the Zoom meetings. It says 7 o'clock on there, but Zoom is limited in the number of times that you can do that, so it's a 7 o'clock block, but you don't have to be here until 7:45. So log on from wherever you are. That's a couple minutes before 7:45, and then at that point, the material that's supposed to be covered that day, and so I'll be adding, rather than modifying the schedule, which I probably will do also, but what I'll do is on Moodle, this is my other task over spring break. So today on Moodle, there's a new R script and an updated P's file that you need to be paying attention to. So in the same way that I've been putting things on dates, what I'll do there is I'll just, on the dates that we would normally have class scheduled, I'll just put a little note there. This date, have this screencast watched. I can put a link to the actual screencast that's on the YouTube site in there. So that's the one that you need to watch prior to coming to class that day. And then the whole purpose of that time is going to basically be to use that time to make sure you understand what the material was in that screencast, answer questions, et cetera, et cetera. I think that's gonna be a more efficient time of our video chatting time than me delivering the information to you in that venue. Once again, I'll be at my computer. I will be able to do, show you the screen that I'm working off of, so that if we need to go back and re-explain things, I can either do that using the PowerPoint, or I can switch to my camera and do it showing you the screen, showing you a whiteboard in my office or something like that.
So during the Zoom session, can you see us?
I don't have to see you, so you get to choose whether or not you have your video on. Really, the most
Or
important,
my pajamas or?
the most important thing for you, the most important, at 7:45, I'm gonna have questions about you. The most important, you have toothpaste around your lips.
Fun.
Yeah.
It's that kind of day.
It shows that you brushed your teeth this morning, having good
There's the guy.
So the most important thing for you is for you to see my computer screen and to see my whiteboard. I don't necessarily need to see you at all. So if you want to be in your pajamas, that's fine. If you want us to see you in your pajamas, turn on your camera. I will more than likely be always screencasting from my office, especially during the 7:45 hour, because there won't be so many users up here that the internet connection will start to get bogged down. By 12:30 animal behavior class, I probably will be screencasting from my house, because that's in the middle of the day when a lot of other courses are offered. And I already have trouble sometimes uploading videos and stuff like that from school because the internet's slower than my home connection. So I will probably do that from school, but for this one, I'll probably do it from campus. So it doesn't really matter where I am. I can do it from a Starbucks if I felt like it. So for those 2 weeks or beyond, and I suspect it might be beyond if you look at the path that this is taken in China. First appeared in China back in January, and while their cases are still going down, they still have those parts of China that have been most affected are still locked down. So I would be probably a little surprised if we all came back to school on April 5th. But so I'm kind of operating under the assumption that this is probably going to be an extended thing. Yeah.
I was just gonna ask for professional advice on that. I mean, we see China's curve, right?
Yeah, so I think China is a good thing to look at, though one of the things that is different about China from the United States is that having a centralized government that works, they actually did centralized government sorts of things, such as quarantining an entire region of China.
Yeah.
Which we have not done here. Another problem that we have here is that we don't have widespread testing. And so you guys might have heard that Tom Hanks and Rita Wilson were diagnosed with COVID. The only reason that they knew that they were infected is that they got screened as they were entering Australia, where testing is much more widespread. South Korea has a much lower death rate right now, but the reason that death rate is so low that they have a relatively small number of deaths compared to the hundreds of thousands of people that they have tested. And so they've tested hundreds of thousands of people. They have a much better handle of how this is circulating in the community.
It is more
As a
precise.
result, the number of people who have died per number of people that they know for a fact are infected is way lower. Our death rate is like 5.86 or something like that last time I looked, 5.86%. But the death rate is the percent who die who have been verified to be infected.
And we have a low
That-
denominator.
We have a really small denominator because we're really only testing people who have shown signs of being sick. In South Korea, they're randomly testing people on the street. They have drive-through, they literally have drive-through testing centers. You drive up, you fill out a questionnaire, they take swabs, they put them in a case, they send them off to a lab, they get tested in 2 or 3 days. You get a report back in the mail as to whether or not you're positive. And so mortality rate, which is calculated differently by health centers, is actually the number of dead per population. And so our mortality rate is probably similar to other countries. Our death rate is higher because we know how many people have died. We have no, I could use an expletive, clue as to how many people actually are carrying it around. And this is bad because there are a number of people, including people your age, who might be exposed to it, but aren't showing any symptoms because you just haven't manifested yet. And you may never develop really strong symptoms. And so the fact that we don't know at broad scales who is infected or not is really problematic in the United States. So we could look to China, but China, because of its political structure, its governmental structure, can do things like take the Wuhan province and say, everybody in Wuhan, stay in Wuhan. You can't tell everybody in Kansas City to stay in Kansas City and don't leave in this country. And even if we did, exert emergency powers and things like that, Americans are notoriously non-compliant. And we're not testing adequately, and so we don't know who we need to be taking care of. We don't know who we need to be quarantining, et cetera, which is why colleges and universities are doing things like what we're doing, which is basically get you people away from one another. Because the closer you are in proximity to one another, the more likely you are to transmit a disease from one person to another. This is why college campuses generally have higher rates of disease transmission than other places, because we cram you together, 2 students in a 6x10 room or whatever it is that you live in the dormitories, and you're all in one building with common circulation system, et cetera, and so, when flu comes to the campus, it tends to circulate through dormitories simply because you're all in close proximity with one another. So what you need to do is we need to just spread things out, get everybody, as far away from one another as possible, which is why, the basketball playoffs in college have been done away with. I don't know why our athletes are not here because yesterday afternoon the college canceled athletic competitions. So where are those athletes who should be here now?
They're on the road to a baseball game.
Well, except that they shouldn't be on the road on a baseball game because yesterday Jewel canceled all athletic competitions.
They're afraid.
So
cough.
anyway, what I will do is I will post screencasts. They will be posted at least a couple of days. A good number of them should be posted over spring break. My goal is to get a couple of weeks out in front of this. So view the screencast before we're scheduled to meet online about it, and then come with questions about the information that was in the screencast, and I will do my best remotely to get those questions answered. All assignments will now be done electronically. I know some of you are already doing the current assignment on Excel spreadsheets, which is fine. Make sure that you're doing it in such a way that I can see your equations. Tom had a question about conducting Levine's test, and I was able to go into the spreadsheet that he sent me and look at his equations. And when I looked at how he had his equation set up, I could figure out what he was doing wrong. I corrected it, and then it corrected itself, evidently. So the equations are important for 2 reasons. One, I can tell that you know what you're doing, and 2, I can also diagnose why you think you're getting an answer that isn't the correct answer. And so On the website, I've also, on the Moodle site, I've also given you, the ANOVA report that's due the 27th of March. This is gonna be in the form of a written report. The PEAS data set that we're going to go through today in great detail, I have a written report already for the PEAS data set that shows you kind of how I want this formatted. I'm gonna go in and make a couple of changes later on today on that and get that posted, so that when I say I want a written report, you will be able to see what that written report looks like, so you can just kind of copy that format. Talking about statistics isn't that difficult. The key to talking about statistics is just translating it into language that somebody who doesn't know about statistics can understand. And so today we have two things I want to go through with you. I want to talk to you about plan comparisons, which will be pretty quick, and I want to talk to you about post hoc tests, and then I want to take you all the way through the PEAS analysis. And I've placed the full R script for the PEAS analysis is actually in this materials for 13 March 2020. If you haven't pulled that up yet, go ahead and pull that up and have it available. We'll be dealing with that here in a while. Yeah.
That has the same name as previous files we've dealt with.
Yes, it does.
Is it the same file or is it
It's not, which is why it's an updated file.
Okay, but if I download that, it's gonna overwrite my old file, right?
That's fine. This is a better, more complete version of it.
Yeah, but I used that other file.
Then just then download it to, for example, your downloads folder. In your downloads folder, change the name of it, and then copy it into the folder that you have your stat stuff in.
Okay.
So just rename it.
Okay.
Yep. That's easy.
How about this CSV file?
CSV file. The CSV file is also different in that it has contrasts in it for doing plan comparisons, and the old version did not.
All right.
So after you've done an ANOVA, and you find that the ANOVA is significant, you should only do comparisons among treatment means after you've observed an overall significant ANOVA. If the overall ANOVA is not significant, there aren't differences among the means, so it makes no sense to go and test for differences among the means. And so there are two kinds of comparisons you can make. You can make plan comparisons. Plan comparisons are comparisons among groups that you anticipated wanting to know about. And these should be orthogonal. Orthogonal just means that they are independent of one another. And I'll show you how to calculate orthogonality when we get to it. Unplanned comparisons are for those kinds of questions where you didn't have any a priori or before the fact idea of what might be different from what. And so you're just interested, okay, I saw that some means might be different, which means are different, and is that really informative to me or not? In both of these situations, you want to use methods that preserve experiment-wise alpha level. So if you did a set of t-tests, so you said, oh, there are five different means. I know that some of these means are different from one another. What I'm going to do is I'm going to do 10 t-tests to evaluate whether these 10 comparisons that come out of these 5 treatments are actually significant. That would be a way of doing this that basically inflated your experiment-wide alpha level to 50%. The methods that we're going to use don't do that. So you can still make these comparisons, but your overall p-value still stays at 5%. So you're not mistakenly saying that two things are different when in actuality they're not. So we are going to use plan comparisons, does that automatically. The post hoc test that we're going to use is referred to as 2 keys on a significant difference test. it has pretty good power, and it tends to avoid type 1 errors pretty well. And so almost any time you see somebody doing post hoc comparisons, they're going to be doing a two-piece test on this stuff. So let's just go back and remind ourselves of the pea example. We have these pea shoots that were grown in different medium infused with different kinds of pure sugars and sugar mixtures. The response variable is the shoot length. You might have some planned comparisons before you even analyze the data. And in this case, the researchers did. They were interested, for example, in is the control different from everybody else, all the other treatments. They also had a hypothesis of are pure sugars, 2% glucose, 2% fructose, 2% sucrose, different from mixed sugars. So are pure sugars different from mixtures of sugars? They also wanted to know whether, well, I don't remember what all their orthogonal contrasts were. We'll get to them in a minute. But these are all kinds of logical things that you might ask.
There's something about a disaccharide.
Yeah. Then there's is there a difference between disaccharides and monosaccharides? So this would be is sucrose, which is a disaccharide, different from the three monosaccharides? So these are kind of logical questions that a plant biologist might want to know.
So you're not doing one-on-one comparisons, it's like you're grouping them as a team.
You're grouping them as a team, yeah. So this would be one treatment versus 4 treatments. This would be 3 treatments versus 1 treatment. This would be 1 treatment versus 3 treatments.
Okay.
The way
They're grouped, just like partnership comparison.
Yeah. So in this case, you're comparing sucrose to these 3. Okay, and those 3 are all grouped into instead of being 2% glucose, 2% fructose, 1% and 1% of fructose and glucose together, these would all be monosaccharides. This would be disaccharides. So you're basically comparing one group to another group, but in this case, one of the groups is made up of 3 of your original treatments. So these are all reasons that you might expect to be making comparisons that you have before you ever conduct the experiment. You already have these comparisons in mind. So what we get when we do this is we have the overall ANOVA. The overall ANOVA was significant, and now these are out of order. And so then what you do is you set up this set of contrasts. So Tom, you played right into my hand. For this comparison, you're basically comparing the control to everybody else. And so the way you set up contrasts for doing this is you give the one thing that you're comparing to everybody else, you give that a coefficient that basically is equal to the number of other treatments that you have. And and this is different from in this thing because I multiplied everything times 4 to get rid of fractions. The control is 4, and that's balanced by a -1, -1, -1, -1, so that this whole thing should always add up to 0. So your contrasts that you set up should always add to 0. But all you're doing when you do this is you're just telling the computer, I'm making all of these things one group. That one group has the name -1. I have this one group that has the name 4, so it's going to compare group 4 with group -1 and do that. The reason that we give them numbers that add up is that we always have to have this thing summing to 0. And so you always know if you've done your contrast correctly, if it is comparing the things that you want to compare and the total column sums to 0. So when we want to compare disaccharides to monosaccharides, disaccharides gets the big number, monosaccharides gets the small negative numbers. You could just as easily did positive 1, positive 1, positive 1, but then in this case this would be -3. Doesn't really matter, it's just coding. But because you know that this all adds to 0, you have done that comparison correct. The control gets a 0 here because it doesn't enter into the analysis at all. Because when you're comparing monosaccharides to disaccharides, the control didn't get any sugars, and so it doesn't get anything. Same thing with contrast 3. In this case, we're comparing pure sugars to mixtures. Mixture versus pure sugars.
Okay, and a contrast is between, there's two sides to that contrast coin, not 3. You know what I mean? Like look over there. You have a equal sign. It's not like you have another. You know, like you're doing some 3-way comparison.
No, these are all pairwise comparisons. They're all
Yeah.
pairwise comparisons, yeah. It's 4 plus -1 plus -1 plus -1 plus -1. This compared to that.
And you're never gonna have some other, you know, this
Nope.
and that and.
No, because
Yeah,
here you're
it's
interested
two-way.
in whether or not groups, if you want to know if this is different from that, is different from this other thing, that's an ANOVA.
Okay,
That's not a clan comparison.
okay.
Okay, yeah, so these are all pairwise comparisons, which is why you should always have one positive value and a set of negative values that are all the same negative value. In this case, we're interested in pure versus mixed sugars, but that are all monosaccharides. Pure versus mixed sugar, pure versus mixed sugar, but all monosaccharides. Here, you're interested in all sugars that are 2%. Some of them are monosaccharides, some of them are, one of them is a disaccharide. So these are the kinds of comparisons that you might want to do. Yeah.
Is there any significance to which side is positive and negative?
Nope, you could, like I said before, you can make the big number negative, but if you make the big number negative, then you have to make the other numbers positive. They just, once again, they just have to sum to 0.
Why you wanna do that?
Why do you wanna do what?
Like labeling the control, the glucose?
For 2 things, if you're doing this on a computer, it tells you that, it tells you which things are being grouped together. In the same way that giving them this label of 2% fructose, it binds together all those observations of those plants that were given 2% fructose. And 2% glucose is a label that binds together all those individuals that are 2% fructose. So it's essentially a labeling system.
So that,
But the reason that we use numbers to do the labeling is so that we can check ourselves as to whether or not we have done our contrast correctly, because if this whole column adds to something other than 0, then we've done something wrong with our labeling of things. The other reason that we do this numbering is we can test for orthogonality. When these plan comparisons, in some books they talk about them in terms of plan comparisons. In some cases, they refer to these as independent contrasts. And what that means is that when you make one kind of contrast, it's independent of making another kind of contrast. They're not nested within one another. And the way you can test this is we have the control, we have 2% glucose, we have 2% fructose, we have 1 of glucose and fructose, and we have 2% sucrose. Contrast 1 is 4 minus 1 minus 1 minus 1 minus 1. Contrast 2 is 0 minus 1 minus 1 minus 1 and 3. The way you test for orthogonality is based on the numerical values of these contrasts. If you want to know if this comparison is independent of this comparison, you take the contrasts and you multiply them times one another. This would then be 0, this would be +1, this would be +1, this would be +1, and this would be -3. Once again, that whole thing should sum to equal 0 if they are indeed independent. So you could do this with any of the contrasts. Is contrast 1 independent of contrast 3? Well, what are the contrast 3 coefficients? 0, -1, -1, +3, -1. Once again, this is 0, this is +1, this is +1, this is -3, and that is +1. Once again, that sums to 0. That contrast is orthogonal. Is contrast 1 independent of contrast 4? Well, what are the contrast coefficients? 0, -1, -1, +2, and 0, because it's not including sucrose. This would be 0, +1, +1, -2. Once again, that sums to 0. That one is orthogonal. So the other reason that we use these numerical coefficients is it allows us to make sure that we are making comparisons, these multiple comparisons in ways that are independent from one another. And so this is just the easy way to test it out. Here's the other thing, though. You cannot have more independent contrasts than you have treatments. So in this case, we have 5 treatments. You can only have 5 contrasts. You've now used up all of your degrees of freedom for making comparisons. I have done this, and in the data file, in the P's data file, if you want to play around with this, you can make 7 contrasts. So I've set up 7 different contrasts. You can do that, but R will only let you do the first 5 in the list. So if you try it, just do it as a test in the script that I've written. Try and add the other contrasts, and when you do that, R will complain to you that you're doing something that you can't do, and then it will also just refuse to do it. It will only do the first 5 that you have listed.
And why is it doing that? What's the downside?
You run out of degrees of freedom. You don't have any more degrees of freedom to make tests.
Okay.
This is easiest to do when you're doing doing it on the computer, but it's basically just calculating a set of F statistics. And in this case, you have sums of squares of a treatment, and in this case, the treatment sums of squares would be the difference between this and the grand mean, and the difference between the mean of all of this and the grand mean. But because you only have 2 means here, the degrees of freedom is going to equal to be 1. So the sum squared treatment is also the same as the mean squared. And so that's one of the nice things, that the math is a little simpler. But the F is still calculated as the mean squared treatment divided by mean squared error. So it's just doing a set of pairwise comparisons that you're analyzing the same way that you did the whole big ANOVA. So there's nothing really different or complicated about the math. It's the same thing that you've always been doing. So that's plane comparisons. You're limited in the number of comparisons that you can make. That limit is ultimately imposed upon you by the number of treatments that you have available. Questions about that? All right, now let's talk about post hoc tests. Post hoc tests generally allow you to make all possible pairwise comparisons. So in this case, it would allow you to compare control to 2% glucose, control to 2% fructose, control to 1-to-1 glucose fructose, control to sucrose, glucose to fructose, glucose to 1-to-1, glucose to sucrose, fructose to that, this to that. 10 different comparisons. And it allows you to do these simultaneously, and it controls for experiment-wide alpha level. So the way you do this is with a thing called Tukey-Kramer's on a significant difference test. And it uses a bunch of information that you already have available to you. And what you're trying to do is you're trying to calculate the minimum significant difference or the on a significant difference. And the way that you do this is you get a critical value, which is a thing called Q, which I'll explain in a minute, and you need to know what the standard error is. And all you need to know for the standard error is what's the mean squared within, and what's your sample sizes that you're dealing with for any pair of combinations. So this thing Q is called the studentized range statistic. I occasionally come to class with a little book that is a table of statistical tables. You can look this up in Wolf and Sokol's book of statistical tables. It's actually table J. So you can look this up in a table. The other thing though that you can do is you can just go to the web and say, I want to know what the studentized range statistic is. And somebody has built a studentized range statistics calculator that turns out to be correct because I've tested it. K is the number of treatments. Degrees of freedom is the degrees of freedom for sum squares within, so it's the error degrees of freedom, sum squared error or sum squared residual. So for the P's data set, we have 10 observations in each of 5 different treatments. We have 50. Our total sample size is 50, which means that our total degrees of freedom is 49, because it's 1 minus the total. We have 5 treatments, which means that our treatment degrees of freedom is 4, and 4 minus 49 is 45. This is our error degrees of freedom. We could have also calculated error degrees of freedom by basically taking the entire data set, sum of all the n's for all the treatments, minus the number of treatments that you have, which would be 50 minus 5, which is also 45. It doesn't matter how you calculate it, this is the error degrees of freedom. So the error degrees of freedom here is 45. We have 5 treatments, and we're going to test at Q of 0.05. So if you put 5 in there, you put 45 in here, and you calculate that, it gives you 4.02. So Q in this case is 4.02. So easy enough to find this out. Just search for this website. Just ask the internet for the studentized range statistic calculation, and this will be the second or third link that comes up. Once you have that, the rest of this is fairly easy. All you need is the mean squared within, which is on the previous frame here, it's 5.46. So if you want to know what the minimum significant difference is, or the odd significant difference is, it's Q plus the standard error is the odd significant difference that you're looking for. And so the critical value here is 4.02 multiplied times this thing is the square root of the mean squared within times 1 over n1 times 1 over n2. In this case, they're the same sample size for all pairwise comparisons, so this is 10, that's 10, divided by 2.
Is that a times or a plus?
That's a times.
No, outside the,
This is a times also.
if you go up one line.
Oh, that's a plus, cause I screwed that up.
Okay, got it.
Yep. So this would be 4.02 times the square root of 5.46 times 1/10 plus 1/10 divided by 2, so that is 4.02 times 5.46 divided by, well, multiply times 2 divided by 10, all divided by 2 square root, which this then equals 4.02 times 0.7389. So the minimum significant difference is 2.97. That's how big your differences have to be, differences among means have to be. They have to be that big or bigger in order for you to say that they're different from one another. Yeah.
Where did you get the 4.02?
I got it from calculating Q,
Okay.
which is what we did on some website that somebody gave us a calculator. Okay? Yep. That's Q, so. So now we know that the minimum significant difference is 2.97. Now all we have to do is basically say, well, what are our observed differences? Well, the difference between control in itself is nothing. The difference between control and 2% glucose is 10.8. Control and 2% fructose is 11.9. Control and the 1-to-1 is 12.1. Control and sucrose is 6. All of these are bigger than 2.97. Difference between glucose and fructose is 1.1. It's below 2.97, so it's not significant. 1.3 is below 2.97. 4.8 is above 2.97. Difference between 2% fructose and the 1-to-1 of the two mixtures of the mixture is 0.2. That's below 2.97. So you're basically comparing, is this value that we observe different from this value? Is this value that we observe different from this value? Is this value different from that value? Is this value different from that value? All these values are the same, it's 2.97. So you're just looking at the pairwise differences and saying, are they bigger than the minimum significant difference, or are they less than this minimum significant difference? So this,
If it's less than the minimum,
then they're not different.
you didn't reach the threshold, and so you can't reject the null hypothesis, and they stay the way they are. Which
They're
is-
not
They're
not different. And so this honest significant difference that you calculate is actually a difference in terms of the differences among the means that you're comparing to one another. Yeah, Brooks.
Where did those, the red numbers in the lower left side of that table come from?
This is 70.1 minus 59.3.
Oh, gotcha.
70.1 minus 58.2. It's just really, it's the differences among the means. So when we talk about honest significant difference, this difference is mean 1 minus mean 2. It doesn't matter which one you subtract from which one, but then you have to do just the absolute value of the difference.
So that was the MSD, this table is the HSD, or the other way around?
No, the MSD and HSD are the same thing.
Okay.
It's just depending on the book that you use. This is the observed difference. This is the criterion that you have to overcome to say that two things are different. So these are, the lower left-hand side of this table is the actual differences. The upper half is the minimum or honest significant difference that you have to compare it to.
Okay, and where did the observed differences come from?
Just subtracting one mean from another.
Okay, and where did those come from?
Well, they came from the table of means.
Table of
Go back 2 frames.
Got it, okay.
70.1 minus 59.3.
Okay.
70.1 minus 58.2, 71 minus 58, 70.1 minus 64.10. So it's just the pairwise differences of means. It's up here, Tom. This difference is differences among means.
Okay.
And those differences have to be bigger than the minimum difference that you calculate. And I don't care how you display the data. If you feel comfortable doing it this way, that's great. I can figure that table out. If you want to just plot things on the plot, showing me what differences are significant, I'm good with that also. Now, this doesn't tell you what the actual p-value is for any of these differences. All you know is that the p-value is below 0.05. The computer output will tell you what the actual p-values are, but you don't necessarily need to know them. You just know that for the Tukey Kramer test, all the p-values are below 0.05. If you calculated Q, at the 0.05 level, if you calculate it at the 0.0 level, then Q is going to be bigger, which means that the difference that you observe has to be bigger, because you're going to be multiplying instead of 4.02, you're going to be multiplying this times 4.89.
It's a tougher test.
It's a tougher test because the alpha level is smaller, which should make intuitive sense to you at this point in the semester, hopefully. Oh my God, that concludes ANOVA. I feel like we've been in ANOVA land for forever. After you come back from spring break, we're going to do a two-way ANOVA where we're looking at data that are classified by two categorical variables. One treatment type versus another treatment type. Same concepts that we use in a one-way ANOVA also get used in a two-way ANOVA. It's just that the way you do the calculations are different because you have two ways of classifying the data. So if you don't know how to do a one-way ANOVA, when you start working on a two-way ANOVA, you are totally screwed. So it's important that you understand one-way ANOVAs really well. Athos.
Can you give us examples of cases, like for the conclusion parts? Because I feel I can do this math with the formulas, but if once I reach the HSD, I don't know what to do with this number. What conclusion should I take
You say,
to
this
reject
is,
or not the null hypothesis?
this is the minimum difference that you should observe. If the difference that you observe is bigger than this difference, then those means are different. If the difference that you've calculated is bigger than the difference that you observe, then you would say they're not different. So going back to this table, going back to this table right here, these are the observed difference between the control and 2% glucose.
Yes.
10.89, bigger than 2.97?
Yes.
Different. Bigger than 2.97?
Yes.
Different. Bigger than 2.97? Different. Smaller than 2.97?
Yes.
Not different. So 2% glucose is not different from 2% fructose. 2% glucose is not different from the one-to-one mixture of the two simple sugars. So it really is, this is the difference that you're looking for. If it's bigger, they're different. If it's not bigger, they're not.
It's like you've done an ANOVA just for those two.
It's kind of analogous.
Okay. Now, that chart right there, I can understand how to use that,
Yeah.
but that doesn't look like what the R script, the Tukey
No.
result of the R script.
No, but it is in that when you do a Tukey's test on the R script, it gives you, is treatment B different from treatment A? You have a p-value that tells you it is.
Okay, that's
Is
how you-
treatment C different from
that's how you
treatment A?
interpret it.
Is the p-value different? Yeah, and we're about to run an R script on this
Okay,
piece of
okay,
data.
good, good, good.
Okay? If we've got all of our other questions answered, we're gonna run the script here in a minute. Everybody good?
Wait,
Yeah.
one more question.
Right.
Going back a little bit, what values were the
These are just the sample sizes of whatever two means that you're comparing. In this case, it's really easy because all of our sample sizes are 10. But for the tick data set, you might have a sample size of sample one that is 6 and a sample size of another that is 12 or something like that. In which case, if sample sizes are uneven, then you have to calculate this specifically for each comparison that you make. Which means that these aren't all gonna be 2.97, they're gonna be slightly different because in some cases, you're gonna be comparing a sample size of 6 to a sample size of 12, you might be comparing a sample size of 10 to a sample size of 12, sample size of 8 to a sample size of 6, whatever it happens to be. So this becomes a little more complicated if you have unequal sample sizes because each of these values is going to be different and you have to make sure that you're comparing 2%, so you're taking control versus 2% is here, and control versus 2% is here. You have to make sure that you're making the right comparisons. So, this is why you should always struggle to have balanced designs rather than unbalanced designs, because it makes the calculations more complicated. But all it means is that instead of having a table where half of it is all one number and the other half is observed numbers, you have one half that is a bunch of different calculated numbers and the other is a bunch of different observed numbers. You just have to be careful that when you're comparing control 2% fructose, that you're comparing it to control 2% fructose. Once again, it's just minor irritation. But the equation still works. You just have to pay attention to sample size. All right. Other questions? That's actually a really good question. All right.
Break.
Break? You're about to get a break. You're about to get a 3-week break.
The 14 days quarantine.
All right. So here's the P's data analyzed. Bigger, not smaller. So this is one of the most heavily annotated scripts I've ever written. So you should be able to walk through this, just read the green text and it should tell you what's going on. So for example, I don't even get down to testing to see where I am on my computer until line 26. So I get my working directory. My working directory is correct. I'm going to bring the data in. This is the P's data set. I'm going to check to make sure that it is correct. And what I have here is I have treatment, which is the original treatment. I have the growth increment, and then I have a bunch of contrast coefficients. These are the contrast coefficients that are from the PowerPoint that we went through earlier. I also have a thing called treatment A that I just added because it's easier for me to do it this way than do it another way of ordering my treatments when I go to make graphics. So I want my graphic to be arranged in a particular way, and so let's just do capital view dat, and when we do that, it opens it up in a separate table in the space above. And so you can see that I have control is treatment A, 2% glucose is B, 2% fructose is C, this is D, and that is E. When R calculates things for you, it gives you output in the order according to the alphanumeric label that you have on things. And so it's going to take this 1% glucose, 1% fructose, and it's going to put it first. And I want control to be first, so I've just given my treatments different labels that keeps them in the order that they are in the data set originally, A, B, C, D, E. So it's basically an indexing thing. There are other more elegant ways of doing that, but I did this a long time ago. Whoa. So now I'm loading packages, I don't know why. I have X's here. ggplot, RMS, car, and tidyverse. You should need all of those. The next thing I want to do is I want to make sure that it's classifying my treatments and my data correctly. This should be a factor, that should be an integer, so that all looks good. First thing you always want to do is you want to check the assumptions. Why?
All those red X's.
I have no idea. It just ran this right before class, and it's running fine. R is stupid. So once again, I'm testing normality. I'm getting the residuals for all of my treatments simultaneously. Then I'm testing those residuals using a Shapiro-Wilk test. And the Shapiro-Wilk test is not significant, and the data don't look very different from normal. There's a little bit of skew here, but it's not enough skew that is pulling this away from the computer, concluding that it is normal. We can do a QQ plot, which once again shows that most of the data are arranged along the line, and it's the deviations from the line that indicate generally that you don't have normal data. You can do this for each treatment, and what you're gonna find is that they all have p-values below 0.05, or sorry, above 0.05, which once again means that on a treatment by treatment level, there's no evidence to suggest that there's any deviations from normality. We can run a Levine's test, but then we start to have a problem. And the problem that we have is that we observe that at least one of the variances is different from some other variance. So we have a p-value of 0.003, which means that we have a significant deviation from homogeneity of variances, meaning our variances are different. So what we have to do when we do that is we have to figure out a way of making our variances more equal. And in this case, the transformation that works is basically dividing the growth into 1 and multiplying times 100. And so this is a little code that's basically creating another column in our data frame. So I'm going to basically ask it to take the data frame, add a new column to it, and in that new column, I'm going to ask you to do this equation and round to 2 decimal points, is what this whole thing is basically saying. And you can also see that there's a really long explanation here explaining what this line of code does. So
you're just numerically tweaking the data so it's got less variation?
Yep.
You can do that?
Yep.
And,
Yeah.
and results are still,
That's cheating.
yeah.
No, it's not. Look in your book, go to the index in your book and look up data transformation or just transformation. There's a whole section in one of the chapters that talks about different transformations. Depending on the shape of your data, there are certain transformations that are fairly standard. If your data are right skewed, logarithmic transformation or square root transformation oftentimes brings that tail in, takes those really big numbers and brings them in while not changing the small numbers very much at all.
So we're gonna run a Levine, looks like next up, we're gonna run a Levine test on some transform stuff.
Transform data, yep.
And the answer will still be the same as though we.
Nope. The answer will be different because now, not significantly different from.
But it's not the same data. It's
Okay, just hang with me.
Okay,
So-
but right now, we're in this alternate transform universe, right?
So it's the same data, it's just data that you've done manipulation to. We can get back to the original data. How can we get
Okay.
back to the original data?
Okay.
Just multiply it times 100.
Okay,
It's easy.
You have the data, you punch the data, now it's different.
Yes, but I can unpunch the data and the data will go back to the way they are.
But why you want to punch the data?
Because if the data have variances that are different, it's harder to make clear decisions about whether the means are different. Going back to stuff that we covered in the first 4 weeks. And I prefer to not think of it as punching the data. Because when you punch the data, you have a black eye,
Okay.
and the data don't have a black eye.
You're putting makeup on the data.
Transform it. Transform.
Let's put some fashion on
The
it.
data was a frog, then the princess kissed the frog, turned the frog into a prince. But then, the princess really didn't love the frog, and so that broke the spell, and the prince got turned back into a frog. This is
Okay,
a better
okay.
analogy.
Okay, but while it's a prince, we got PR of .1074.
While it's a prince, we're gonna have sex with that prince.
Maybe clean up that.
Because the prince meets all of our requirements that we want in a prince that we want to live happily ever after with. It's normally distributed and it has variances that are equal. The reason you don't want variances to be unequal, here you have two populations, one with a small variance, one with a large variance. If we look at the means of these, this mean could easily fit within this population, but this mean does not fit within that population. So when we have unequal variances, it makes it difficult to decide what's the right answer. Are these means different or are they not? Can't tell. Let's transform this data. I'm assuming that everybody wants to have sex with the prince. Let's transform this data from data that have heterogeneous variances into data that have homogeneous variances. Then we can run our tests on that transformed data, but then the conclusions that we get out of that are now valid because we've checked off all of the check marks. The data are independent, the data are random, the data are normal, and the data have homogeneous variances.
Because the data was manipulated.
Yes, they are. But there's nothing wrong with the manipulation.
There's nothing wrong with manipulation.
Because all we've done is we've made the data conform to the requirements of the test. If we don't do this, we can't depend upon the answers that we get. The answers that we get might be wrong
Yeah.
in terms of the relationship among the means. So all of our assumptions are checked off. They're all checked off. If we didn't do this, that one would not be there, and this is actually the most important one of all of them. This is the one that messes you up in making the right decisions most often.
So we transformed the data, we got the answer we were looking for, which is a large P.
Yep. Now,
Meaning it's homogeneous.
all of the treatments have similar variances. So now that we know that, we can look at this. So now we're analyzing this column of data, not that column of data. So we can get a table of means just to see what it looks like. It's got the Transdat data. Once again, you can see how this has rearranged the order of things in ways that I don't want, because I want glucose to come first, et cetera, et cetera. That's why treatment A is in the data set. So we can get it with treatment A, and it now has just this is now controlled 2% glucose, 2% fructose, 1-to-1, and sucrose in the right order. So we can run an ANOVA on the transformed data. And when we do this, we find that there are differences among the treatments, which should be apparent to you from when we've looked at these data.
So we have to stick with it, at this point, we still have to stick with the transformed data.
So when we look at the data in this form, it's clear that some of these treatments are different from others of these treatments, and the analysis of variance has just confirmed that. Okay? So, we have some means. So if we go back up here, we have means, and we have confidence intervals, the distance above and below the confidence intervals. Matt?
So does it matter that the F value we got for the ANOVA is different than the F that we got for the Levine's test?
Yeah, because the ANOVA is testing for differences among means. The Levine's test is testing for differences among variances.
Okay,
So,
I
yeah.
thought you said the other day that they were supposed to be the same.
Okay.
No. the funny thing about Levine's test is Levine's test is basically just doing an ANOVA on the residuals rather than doing an ANOVA on the raw value. So the calculations are exactly the same, it's just the data that it's working on that's different. We're out of time, so what I want you to do over spring break is after we run the ANOVA on the transformed data, we have to go through and do plan comparisons. This is how you build the matrix for doing plan comparisons. It's a little complicated in how you make it happen. Then you do those plan comparisons and it'll give you an ANOVA. But then, after you've done all of that, you can run in 2-keys if you want to. You can test that a couple of different ways. This is 2-keys analysis using, I think, the standard base R. This is a different program that does the same thing. Should give you the same answers. But then what you want to do, and this is getting to Tom's concern, is now you want to take the transform data and put it back in the original units. And so I make a plot with the transformed data, and then I go through and I then back transform the data. This is the back transformation. And then I create another plot that then has the statistical results that are plotted in the units of the original data.
The original thought.
Okay.
You compare both distributions?
No, I would just use the last figure. I give you the middle figure because when you look at the middle figure, things that were high in the original data are lowest. So they look like mirror images of one another.
Okay.
Right. So work through the rest of that. As you're working through the script, work through it line by line and read the comments. Don't just go zipping through there, hitting return. I want you to understand what that line of code means, all right? That's gonna be crucially important when you can't just drop by my office to ask a question. Those comments are in there for a reason. Pay attention to the comments that I've done. Heavily annotated scripts, it should describe in pretty good detail what I'm doing and why I'm doing it.
In the problem set, the problems asked us to do the appropriate post hoc.
Yep.
Something or other.
Yep. So if you
That is the 2-key HSV thing?
in all of these, it's the 2-keys because there weren't any specific hypotheses that I said you should be thinking about. But if the researcher came to you and said, I'm really interested in these comparisons, then those would be planned comparisons. And so you would set up contrast, and you would do a contrast.
Okay, so plan comparison is a,
It's-
they're not post hoc.
It's an appropriate,
It's a post hoc thing.
it is a post hoc test, it's just post hocs that you planned versus post hocs that you did.
Got it,
Yep.
okay. But for this problem set, it's just the.
It's just all 2-keys, because most people don't have plans,
Right, okay.
sadly. Bryce, do you have a minute?